Hello, welcome to Calculus with Calculiz. On today's episode, we'll be learning about power series. No superpowers required. You may be thinking, what the heck is a power series anyways? A power series, by definition, is an infinite series in this form, which is the summation from 0 to infinity of a of n times x minus c to the nth power, where a of n represents the coefficient of each term, where n represents the number of terms, and c where the series is centered. For example, here's a power series centered at 0, also known as a Maclaurin series. It is the summation from 0 to infinity of a of n times x to the nth power. As you can see, this can also be written as x minus 0, because c equals 0. Now there's a few things you need to know before we start working out any problems. You need to know about the convergence of a power series. Warning, I may sound like a talking textbook for the next 30 seconds. The convergence of a power series has a few rules. For a power series to be centered at C, 1. The series converges only at C. 2. There exists a real number, r, greater than 0, such that the series converges absolutely for the absolute value of x minus c less than r, and diverges for x minus c, the absolute value of that, greater than r. And 3, the series must converge for absolutely all x. Now r is your radius of convergence. And here, as you can see, I wrote r equals. These are two important radius of convergences that you'll need to remember. I often get them confused, but they have specific times when they'll show up. So, the radius of convergence equals 0 when the series converges only at C. And your radius of convergence will equal infinity when the series converges absolutely for all x. Now try to keep that in mind. Sometimes you may confuse them, but it'll be okay. Now, after learning all that information, we're finally ready to start working out some problems. We're going to find the radius of convergence of this series. We have the summation from 1 to infinity of 4x to the nth power over n squared. Now to do that, we're going to use the ratio test. And the ratio test simply says that a series converges absolutely if the limit from as n approaches infinity of the function with n plus 1 plugged in for n, it's basically just a subscript, over the function, the absolute value of that, is less than 1. So, we're going to do just that. I'm simply just going to rewrite this. Limit as n approaches infinity of the absolute value of u n plus 1 over u n. And we're simply just going to plug in. So, limit of n as n approaches to infinity. I keep messing that up. And we're going to plug in n plus 1 wherever we see n for our series. So, 4x to the n plus 1 over n plus 1 squared over the original function. 4x to the nth power over n squared. Don't forget the absolute value. Alright, so now I'm going to simplify that by multiplying by the reciprocal of this bottom function. So there's absolute value of 4x to the n plus 1 over n plus 1 squared times the reciprocal of this, which is n squared over 4x to the n. Okay, now what you're going to do is simplify it further. Okay, so 4x to the n plus 1 can also be written as 4x to the nth power times 4x. Because when you multiply bases that are the same, you just add the exponents. N plus 1. Alright. So, now that we know that, we have limit as n approaches infinity of 4x to the n times 4x times n squared over n plus 1 squared times 4x to the nth power. And would you look at that? We can cancel out 4x to the nth power and 4x to the nth power. And it'll equal 1. So now we're left with the limit as n approaches infinity, 4x times n squared over n plus 1 squared. So now we're just going to take the limit as n approaches infinity, and as you can see, these two have the same exponents of squared, and the limit is going to go to 1 because these exponents are the same degree, and it's the highest degree. So those will end up going to 1. So then you're left with the limit as n approaches infinity of the absolute value of 4x. Now, we leave the absolute value sign, and we're going to continue to use the ratio test. So, what did it say? It said that it converges absolutely when it's less than 1. So we're just going to set 4x, the absolute value of 4x less than 1. And we're just going to do some simplifying and divide the 4. So we're left with the absolute value of x is less than 1/4. And there you go. This is your radius of convergence. Let's try another example. This is fun, isn't it? Alright. So here we have the summation from n equals 0 to infinity of x to the 2n power over 2n factorial. Ooh, this one has factorials. Nice. Alright. Just like the previous problem, we're going to use the ratio test to determine the radius of convergence. So, again, we're going to use the limit as n approaches infinity of u subscript n plus 1 over u subscript n. And now we're just going to plug n plus 1 in for any n. So, we'll have x times 2 times n plus 1. You got to be careful with this. It's not just 2n plus 1. You want to remember the parentheses here, so you distribute the 2. Alright. So it's that over, same thing here. When you plug in n plus 1, you want to make sure there's a definite, you can see that you're distributing the 2. Alright, so it's 2 times n plus 1 factorial over the original function, x to the 2n over 2n factorial absolute value. Now we're just going to simplify this a little bit and multiply by the reciprocal of this. So the limit as n approaches infinity of, and I'm going to distribute the 2 times n plus 1 for convenience, absolute value of x to the 2n plus 2 power over 2n plus 2 factorial times the reciprocal of this, 2n factorial over x to the 2n. And now, just like the problem before, we have exponents being added. Therefore, we can simplify that and show that the limit as it approaches infinity, that this will equal x to the 2n times x squared, and then times 2n factorial over 2n plus 2 factorial times x to 2n. Alright, so we can cancel these two out since they equal 1. Same thing. Alright, so now we have the limit as n approaches infinity of absolute value of x squared times 2n factorial over 2n plus 2 factorial. Now, for those of you who don't know factorials or need a brief explanation, just to remember, this is a factorial. The exclamation point means factorials. And factorials, you subtract 1 from each term and then multiply it. So 4 factorial is 4 times 3 times 1. You subtract 1 each time, and then you multiply them all together. So n factorial, it's n times, you subtract 1, so n times 1, n minus 1, times subtract another 1, n minus 2. And you're subtracting 1 each time, and you're multiplying them, times n minus 3. And then this just goes on forever. So we have 2n plus 2 factorial. 2n plus 2 factorial. To simplify this further, we'll just subtract 1 each time until we see the pattern and we can cancel them out. So 2n plus 2 factorial equals 2n plus 2 times 2n plus 1 times 2n, and we'll stop there. So this is 2n plus 2 factorial simplified, and we'll just plug that in for what we have because we see that we can cancel the 2n factorials. So let's continue this. So the limit as n approaches infinity, absolute value of x squared times 2n factorial over, and now we'll just put this little piece in, 2n plus 2 times 2n plus 1 times 2n factorial. Now, these just cancel out, and you're left with limit as n approaches infinity of x squared over 2n plus 2 times 2n plus 1. Alright, so now we can start evaluating as n approaches infinity because there's no more left to simplify than that. So you see here, when you plug in infinity for n, you're going to get infinity here and infinity here. And top, well, the top's just going to go to 1. So when you take the limit, you're going to have something over infinity. And when you divide by infinity, you get 0. Mind blown. It's because it's a heck of a small number when you divide by infinity, so eventually it'll end up going to 0. So because the limit equals 0, 0, if we're still using the ratio test, 0 is less than 1, always. So we can conclude that the series converges for absolutely all x, since this holds true for all values of x. So, don't get confused here. Your radius of convergence is going to equal infinity. Don't confuse this with when the radius of convergence equals 0. Just because of your limit equals 0, don't say that your radius equals 0. No, you don't want to mix those two up. Because your limit equals 0, it says that it converges absolutely for all x. Therefore, you want to remember to make your radius of convergence equal to infinity. See, it isn't that bad. Next, we're going to find interval of convergences, which isn't too different from finding the radius of convergence. We're still going to use the ratio test to find the interval. However, we're going to be checking the endpoints, which is very, 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 very important. Alright, so let's do an example of finding the interval of convergence. Let's do this one. The summation of n equals 1 to infinity of negative 1 to the n plus 1 power times x minus 4 to the nth power over n times 9 to the nth power. Alright, this one looks a little crazy, but after you master this one, you can handle almost anything, I think. Alright, so to find the interval of convergence, you're going to do almost the same thing as finding the radius of convergence. So, what we're going to do is use the ratio test again. So, the limit as n approaches infinity, don't forget the ratio test is u of n plus 1 over u of n. So we're going to plug in n plus 1 for each n. They're everywhere in this problem. And then divide by the original function. And to save time, I'm just going to automatically multiply by the reciprocal of the original function, because when you're dividing fractions, you multiply by the reciprocal. And I'm going to do that now. So first, the limit as n approaches infinity, I'm going to plug in n plus 1 for each n. So, negative 1, plugging in n plus 1 here will give you n plus 2 times x minus 4 to the n plus 1 power over n plus 1 times 9 to the n plus 1 power. And now I'm going to multiply by the reciprocal of the original function. So that'll give me n to 9 to the n power over negative 1 to the n plus 1 times x minus 4 to the n. It's all in absolute value symbols. Alright, now let's work some magic and cancel, because there's a lot you can separate and cancel out. It won't look so scary after you cancel things out. So the limit as n approaches infinity of negative 1 to the n plus 2 can simply be written as negative 1 to the n times -1 squared. Because of the bases, you multiply them, and then you add the exponents, which give you this. And then you can do the same thing with this, times x minus 4 to the nth times x minus 4. And then you just multiply across. You can leave the n the same, 9 to the n the same. And then in your denominator you have n plus 1 times 9 to the n times 9 to the first power, which is just 9, times -1 to the n, then times -1, and then times x minus 4 to the n. Whew. Okay, so now we can cancel things out. We can cancel this guy, the 9 to the n, -1 squared is just 1, so we won't have to worry about this guy. We can cancel out the -1 to the nth powers. And I think that's it. And don't forget, we can throw out this -1 because the absolute value of anything is going to be positive. So this -1 won't be applied anymore. So now we're left with limit as n approaches infinity of n times x minus 4 over 9 times n plus 1. Now as we take the limit as n approaches infinity, these n's have the same exponent of 1, so they will end up going to 1 when you take the limit. So then you'll just be left with limit as n approaches infinity of x minus 4 over 9. So, like how we were doing the radius of convergence, we're going to still use the ratio test. So we'll set x minus 4 over 9 less than 1. And then simplify, get this factor out of the denominator, multiply by the 9. So then we'll be left with less than 9. And 9, that means 9 is your radius of convergence. Now, what you're going to do is solve for the interval. So, this can be written as -1 less than x minus 4 over 9, 1. Now you just, since you have the interval, when you see this sign, you know that it's going to be a compound inequality. That's why I wrote it like this. And now you just simplify and solve for x. So you multiply each side by 9. So you have -9 here. X minus 4, 9. Now you just add 4 to each side. So that'll give you -5 here. And adding 4 to this side will give you 13. So here you have an interval, which will also be called your interval of convergence. But wait, we seem to be missing a step. Can you guess what it is? If you guessed that we're missing that we haven't checked the endpoints yet, you're right. And I hope you know to check the endpoints. Even though it may seem tedious, you may not get a lot of points on the AP test by missing out that step, because you won't have the full radius of, the full interval of convergence correctly. So we're going to check the endpoints, and you do that by plugging in each of the endpoints into your original series. to check if it converges at those points or not. And if it converges at those points, it'll be inclusive, and you can write less than or equal to. So let's do that. Let's check those endpoints. So you're going to plug in to your summation the endpoints. You plug them in for x. So let's plug your first one, -5. In for x. Now you just simplify. -1 to the end of 1. This is -9 to the nth power over n to the 9n. So, as you can see here, whenever you have a negative number inside the parentheses to the nth power, you can just extract the negative. And -9 to the n, you can rewrite it as -1 to the n times 9 to the n. So rewriting that, -1 to the n times -1 times -1 to the n times 9 to the n over n times 9 to the n. You can cancel these out. And as you see here, you have a -1 to the n and also another -1 to the n. So those together equals -1 to the 2n, and you still have this -1 there, over n. And when you square that, it's going to give you 1 to the n, which equals 1. So now you're just left with -1 over n. And according to the p-series test, since p equals 1, since p equals 1, and since this is also a harmonic series, it diverges. So your left endpoint of 5 is not included. So we just leave that like that. And now you check your other endpoint, which is 13. So we're going to plug 13 in for x and solve, which is going to give you the summation equals 1, 1, and plus 1. When you plug in 13 for here, 13 minus 4 gives you 9. So you have 9 to the n over n times 9 to the n. And these can cancel right off the bat. And then you'll be left with -1 to the n, which can also be written -1 to the n times just -1 to the first power over n. And here you have an alternating harmonic series. And like we discussed before, harmonic series p equaling 1, it always diverges. You want to remember that harmonic series always diverge. But in this case, we have an alternating harmonic series. Alternating harmonic series that you should have learned previously in other lessons with the series tests, they always converge. Because it converges, our right endpoint of 13 is inclusive. So your interval of convergence is -5 less than x less than or equal to 13. This is your interval of convergence. And you'd write it just like that. We have one final step to make in our journey through power series. Next, you're going to learn how to differentiate and integrate power series. You can relax. If you know how to solve a basic derivative and how to integrate a function, then doing this with power series is no problem. So first, differentiating a power series. Like differentiating a regular function, you know to multiply by the exponent and then subtract 1 from it. So, in this case, f prime of x would equal 2x, and you subtract 1 from the exponent, so it's x to the first power. Simple, right? Now you're going to do the same thing for power series. You have a power series, and to differentiate, you just multiply by the exponent and then subtract 1. So, f prime of x in this case, for a power series, would be n, multiplying by the exponent, times a of n, times x minus c, times n minus 1, because you subtract 1 from the exponent. Now you always want to add 1 to where you're starting from. So we start at 0 for the original, and we add 1 after we differentiated. Because if we kept it at 0 and started at 0, then your exponent would be negative and it would change the value of the whole function. So, let's differentiate this power series. F prime of x will equal summation from n equals 1, because you add 1 to where you're starting from, to infinity, and you take the exponent of the x term and multiply it by your series, and then subtract 1 from it. So here we'll still have negative 1 to the n plus 1 times x minus 1, and we multiply the exponent. So we're going to get times n plus 1 on the top, and our new exponent for x minus 1 will be n, because we subtracted 1 from the exponent. And this is still all over n plus 1. And there you go. That's your derivative. Now I'm going to show you integrating power series. Like integrating a regular function, you add 1 to the exponent and divide by the new one. So, for example, x squared integrated, you add 1 to the exponent, it gives you x to the third, and then you divide by it. Divided by 3. Plus c. Now the same thing applies for power series. When you integrate, you add 1 to the exponent and then divide by the new one. So you'll have a of n times x minus c to the n plus 1, because you added 1 to the exponent, and now you just divide by the new one. So you'll have over n plus 1. So let's do a quick example of finding the integral of a power series. So integrating this will give you, you add 1 to the exponent, so it will be n plus 1, and then you divide by it. So you will have times x minus 2, and you add 1 to the exponent, so it's n plus 1, n, and then you divide by your new exponent, so it's n plus 1 in the denominator. And there you have it. We just learned how to differentiate and integrate a power series. And we also learned how to find the interval of convergence. I bet you would love to know that the integration and derivative of a power series and the original all have the same interval of convergence. That's right, they have the same interval of convergence, except for the endpoints, of course. You always want to test the endpoints to make sure what is inclusive and what's not. And there you have it. Thank you all for joining me on Calculus with Calculiz today. On the next episode, we will be covering conics, be there or be squared.